Good afternoon. Today I just wanted to make a quick little video about written homework 4, the question about what is the optimum volume for this box, or how do we cut up a square piece of cardboard to obtain an optimal volume for a box that doesn't have a lid. So I thought let's start with taking it from a drawing of a box. So here we have a 3D drawing of a box and it doesn't have a lid. You can see inside of it. And we've got the width labeled, the length labeled, and the height labeled. So all in all, my volume equals width times length times height. And from this, you're probably like, yes, Emily, I know, let's move on. But part of what I learned in engineering school, what I learned in boating school, was 3D object visualization. So where I feel really strong in this, you might not feel very strong in this at all. So I just want to make sure that we're going through all of the points so that you don't feel like you got lost. So what we're going to do is we're going to take this box and we're going to cut along these corners and flatten it out. And when we do that, we get something that looks like this little T-shaped diagram. And you can imagine looking at this in, if you have a piece of paper, you can fold it in half, cut some corners, cut some squares out of it, and make it into a box yourself. But so here we have width, height, and length labeled again. And this might be a little bit nuanced to you how I got these. But right here is the base of my box, so that's not going anywhere. So we still have the width, that side-to-side measurement, and the length. And then from here to here, we have the height. And you can imagine kind of folding this back up, taping the corners back together, and getting back to the box that we started with. So the next thing I want to do is use a different color. I think I'm going to use this blue color and fill in to make this one big rectangular piece of cardboard. So here, all right, it doesn't like that. I'm just adding in So if we had a big sheet of rectangular cardboard and we cut this area out, this area, this area, this area, and this area, we cut those away, we'd be left with that T-shaped diagram that I mentioned earlier, and we can fold that up and create a square. So if this was a perfect world, let me draw this a little bit better. I'm going to draw a square. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and back up and over. And I've got my square. And I'm going to say that altogether the length of my square is length L, not to be confused with the length measurement for the volume of my box. And now I want to see, well, can I subtract anything? Maybe I go like this, like this, like this, and I'm saying that I want to get rid of this, 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 and this to get that T shape. I'm going to draw back in the base of my box so I don't get confused. And now it's time to say, well, this length is X, and this length is X. And I don't know exactly how much that is, but I know that L is fixed and X is variable. So I want to reimagine the length, width, and height from before. So I'm going to write those to the side. Length, width, and height. And I want to reimagine those in terms of X and L. And maybe X and L, maybe L isn't the best letter to use, but that's the letter we're going to use. We fixed L. And we're just going to have to move on from there. So the width, let's start with the width. The width is this measurement. And obviously, that's going to be L minus this bit and this bit. And we've already determined that that bit and that bit are X. So our width becomes L minus 2X. Now let's talk about our length. Our length, or our depth, which is probably a better one I should have used, is going to be this measurement. And since we're doing from a square piece of paper or a square piece of cardboard, it's actually going to be the exact same as our width measurement. So it's going to be L minus 2X. And the only thing we really need to worry about is height. Height is going to be something different, and that's from our previous drawing is going to be this measurement right here. So the distance from the base to the edge of my cardboard cutout. So the distance from my base to my cardboard cutout is actually going to be X. So now if I revisit my volume equation, which I have right here, and I paste it right here, volume equals width times length times height. Now all I need to do is replace them with my length, width, and height measurements that I determined. So I'm going to write this as V equals L minus 2X for width, L minus 2X for length, and X for height. Simplified, this is L minus 2X squared times X. And the question is, well, what good does this equation do us? What is this equation? And the answer is that this equation is our optimization. Our optimization function. This is the function we want to optimize. So then the next step that we do is we take the derivative of this equation. And this could be a very challenging step, but you have to remember in this case, L is just some number. Maybe it's the number 9, maybe it's the number 15, we don't really care, but it's a fixed number. It's not changing with respect to time. It's not changing with respect to length. It's not changing. But X, we can vary. X we can make as large as we want, X we can make as small as we want. So what we're gonna do is we're gonna take our optimization function, which I'm gonna highlight, sorry, I'm quite a stickler for picking a good highlighting color. So this is our optimization function. So the very first thing we do is we take the derivative for this one. So we have to use the product rule. So derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, we have to use the chain rule. 2 times, leave the inside, L minus 2X, reduce the power, 2 minus 1 is 1, so we just leave that alone, times the derivative of the inside. Well, L is just a number, so when we take the derivative with respect to X, that goes away. So we really are taking the derivative of minus 2X with respect to X, which just leaves us with minus 2. Times X, because we leave X alone, plus leave the first one alone, times the derivative of the second, which is just 1. So what we're going to do is factor all of these out, right? Or I guess FOIL all of these out is the word that I wanted to use. FOIL all of these out and then find the critical points. And I need to quick check something. I think of you and I believe. Oh, oopsie. So that's what our derivative works out to be. Then all we have to do is find critical points. And here we do have to factor this polynomial, but it factors pretty nicely into v prime equals, let me copy it from my previous work. And I'm going to highlight this one too. Here, it's pretty easy to see that our critical points are going to occur at CP occurs at L over 6 and L over 2. Now, before you go plugging these in and plug and chugging, we want to talk about what this means geometrically for x to equal L over 2. Sorry, let me find. Optimization problems. I apologize for my pause. I'm looking for where this problem comes from in the textbook. Yes. So we're looking for finding the largest possible volume of the open box that can be formed this way. So we're not necessarily looking for these critical points, but we have them. So we've got our critical points, and what do they mean geometrically? Well, for x to equal L over 6, we have, let me draw something real quick. Let's pretend I've got a box. 1, 2, 3, 4, 5, 6. For x to equal L over 6, what we're doing is we're subtracting this portion and this portion away, which means we've still got something right here that we can use to create a width and a height, which is pretty awesome. But for L to equal 1 over 2, all of a sudden, we're doing something like this. And as you can see, if we delete all of this area and all of this area, there's nothing left over. So clearly, L over 2 is not the critical point we're looking for. We're looking for x equals L over 6. So when x equals L over 6, we're going to plug that back into our optimization problem. What's it called? I'm sorry, the word has completely, our objective function. We're plugging this back in. We're plugging x equals L over 6 back into our objective function. So v equals L minus 2x quantity squared times x. V of L over 6 equals L minus 2 times L over 6 squared times L over 6. And now all we have to do is the algebra to figure it out. So L minus 2 over 6 is L minus L over 3 squared times L over 6. L minus L over 3 is 2L over 3 squared times L over 6. And then we square each term, so we get 4L squared over 9 times L over 6. 4L cubed. 9 times 6, I think, is 54. 1, 2, 3, 4, 5, 6. Yeah, 54. So our final volume, the volume of our optimized box, is 4 over 54 times L cubed. And L cubed, and this answer makes sense because we have length cubed, and it's a portion of our full length cubed. You know what I mean? So this is how you pretty much go about solving this problem. I hope that helps.